Do you believe that Earth is essentially a bird trapped inside an iron cage, surrounded by hundreds of tons of shattered debris in orbit, and that a single collision no bigger than 2 dust particles touching is enough to freeze everything? Humanity have never done anything more permanent than pass through on the way to somewhere else. Yet somehow, the sky above us is already full of our garbage. Scientists have been trying to predict this for decades, and the answer they keep arriving at is one that should genuinely stop you in your tracks. Tonight, we are going to find out whether we can still get out of the cage we built for ourselves. But before we go, make sure you have subscribed to the channel. There is a layer of the sky that most people never think about: the band of human-made objects sitting between roughly 336,000 kilometers above the surface of the Earth, orbiting silently at speeds that make the fastest jet aircraft look stationary by comparison, running the quiet infrastructure of modern civilization without anyone on the ground having to notice, or care, or even know the satellites are there. And for most of the past 60 years, that invisibility was considered a virtue. Satellites were designed to be reliable, silent, and unobtrusive, to work in the background while the world below got on with the business of living. The GPS signal that routes you through an unfamiliar city arrives without any indication of the 24 satellites in medium Earth orbit that are triangulating your position to within a few meters. The weather forecast that tells you whether to bring an umbrella is built from data collected by a network of polar orbiting satellites that photograph the entire surface of the Earth multiple times a day. The internet connection that delivers this audio to your device passes through infrastructure that depends, at various points, on satellites handling routing, synchronization, and timing signals so precise that disrupting them would cascade into failures across banking systems, air, traffic control, and emergency communications almost simultaneously. When researchers map the full extent of what modern societies have built on top of satellite infrastructure, the numbers are striking in a way that is easy to underestimate. 78% of commercial aviation navigation depends on GPS. Satellites in polar orbit provide 85% of the input data for global weather models. The models that predict hurricanes, track monsoon patterns, and give agricultural systems enough warning to respond to incoming climate events. As of April 2025, satellite communications networks serve approximately 68% of the global population, meaning 5.56 billion people whose daily access to information, financial systems, and emergency services runs through hardware orbiting hundreds of kilometers above their heads. None of this is secret. The dependency is well documented, widely understood within the relevant industries, and essentially never discussed in public conversation, partly because it has never failed in any significant way, and partly because the alternative, which is imagining what happens if it did, is uncomfortable enough that most people prefer not to linger on it. There is a particular kind of vulnerability that comes from depending entirely on systems you cannot see, cannot touch, and cannot repair from the ground. And satellite infrastructure is the purest expression of that vulnerability that human civilization has ever created. What makes the current moment different from any previous point in the history of the space age is not the existence of that vulnerability, but the degree to which the environment those satellites operate in has changed, and the speed at which it is continuing to change, driven by forces that are individually rational, collectively dangerous, and structurally very difficult to stop. The European Space Agency's 2025 Space Environment Report, which draws on observations collected through the end of 2024, describes the situation in terms that are unusually direct for an institutional document. Earth's orbital environment, the report states, is a finite resource. The number and scale of commercial satellite constellations in certain low Earth orbits continue to increase year over year. Within certain heavily populated altitude bands, The density of active objects is now the same order of magnitude as space debris. And then, in language that deserves to be read slowly, even without any additional launches, the number of space debris would keep growing, because fragmentation events add new debris objects faster than debris can naturally re-enter the atmosphere. Read that again. Even if every rocket on Earth was grounded tomorrow, every launch vehicle, every commercial operator, every national space program, the debris count would still rise. The system has already crossed a threshold where it generates new hazards faster than physics can remove the old ones. That is not a projection about the future. That is a description of right now. To understand why, it helps to know what is actually up there. According to ESA's debris modeling tool, which uses radar observations and statistical models to estimate the full population of orbital objects, there are currently 54,000 debris fragments larger than 10 centimeters in low Earth orbit, large enough to be tracked individually by ground-based radar networks, and large enough to catastrophically destroy any satellite or spacecraft they strike below that size threshold, where individual tracking becomes impossible. The estimated population grows to 1.2 million fragments between 1 and 10 centimeters, objects that cannot be precisely located but are large enough to cause catastrophic damage on impact, and below that, in the 1 millimeter to 1 centimeter range. The estimate reaches 130 million individual pieces of debris, each one invisible to current tracking systems, each one traveling at orbital velocity. 130 million. The number is large enough to be almost meaningless in the abstract. So consider it differently. If you were to count one fragment per second without stopping, it would take more than 4 years to count them all. If you were to lay them end to end, they would circle the Earth more than 3,000 times, and every single one of them is moving at an average speed of 28,000 kilometers per hour, which is roughly 23 times faster than a rifle bullet, and fast enough that the physics of collision stop resembling anything that intuition prepares you for. At those speeds, mass matters far less than velocity. A fragment weighing just 1 gram, traveling at 15 kilometers per second, carries kinetic energy equivalent to a 2-ton rhinoceros running at full speed. A 1 kilogram fragment hits with the force of 22 kilograms of TNT, enough to catastrophically destroy a multi-ton satellite in a fraction of a second, converting it instantly from a functioning piece of infrastructure into a new cloud of high-velocity debris, each fragment of which is now capable of the same thing. This is not a theoretical concern. In 2009, an active American communications satellite called Iridium-33 collided with a defunct Russian spacecraft called Cosmos 2000, 251 over Siberia. The collision generated more than 2,000 trackable debris fragments larger than a smartphone, roughly half of which remain in orbit today, more than 15 years later, continuing to pose collision risks to every other satellite at similar altitudes. And in 2024 alone, several major fragmentation events added more than 3,000 new tracked objects to an already crowded environment. Not from collisions, but from old rocket bodies and decommissioned satellites that were never properly deactivated, slowly accumulating internal stresses until they broke apart, releasing their stored energy as new debris fields that will persist in orbit for decades. The cage, in other words, is not something that will be built in the future. It is being assembled right now, fragment by fragment, at a rate that current mitigation efforts are not keeping pace with. And understanding why that matters requires understanding what happens when the density of that debris crosses a specific threshold that a NASA scientist first calculated nearly half a century ago. What Kessler identified in 1978 was not just a risk, it was a point of no return. And the question that his own updated research published just months ago, is now forcing the scientific community to confront is whether we have already crossed it. In 1978, a NASA scientist named Donald Kessler was working on what seemed, at the time, like fairly academic problem: how to model the long-term behavior of orbital debris populations. Kessler had been applying mathematical techniques originally developed to study the asteroid belt, techniques designed to model how populations of objects in orbit around a central body interact with each other over time, to the growing collection of human-made objects in low Earth orbit. What he found was not reassuring. Kessler and his colleague Burton Corpellet published their findings in a paper titled "Collision Frequency of Artificial Satellites: The Creation of a Debris Belt." And the core insight was this: there exists a critical density threshold for objects in low Earth orbit, above which the collision rate between existing objects becomes self-sustaining. Below that threshold, the debris population is stable. Collisions happen occasionally, but the fragments produce decay out of orbit faster than new ones are created. Above that threshold, the opposite is true. Each collision produces fragments that increase the probability of further collisions, which produce more fragments, which increase the probability further, in a cascade that accelerates exponentially and cannot be reversed by any natural process on any timescale relevant to human civilization. Kessler called this collisional cascading. Everyone else eventually started calling it Kessler Syndrome, and for most of the following 2 decades, it remained in the category of important but distant theoretical concerns. Something to monitor, to study, to eventually address, but not something requiring immediate emergency response. Then the debris population started growing faster than the models had predicted. The 1996 French satellite Ceres was hit by a fragment from an Ariane rocket that had exploded a decade earlier. The first confirmed collision between a catalogued debris object and an operational satellite. The 2007 Chinese anti-satellite test, which we will get to in detail shortly, created the largest single debris cloud in the history of the space age. The 2009 Iridium Cosmos collision validated the cascade mechanism in a way that was no longer theoretical, and by 2009, Kessler himself was writing that modeling results indicated the debris environment had already become unstable, that even a complete moratorium on new launches would not stop the debris population from growing, because the fragments from future collisions between existing objects would accumulate faster than atmospheric drag could remove them. That was 16 years ago. The situation has not improved. In March of 2025, Kessler, now in his 80s, co-authored a new assessment with Hugh Lewis, one of the leading orbital debris researchers in the world, titled "Critical Number of Spacecraft in Low Earth Orbit, a New Assessment of the Stability of the Orbital Debris Environment." The paper used current population data from March 2025 and applied a revised stability model to identify regions of instability across the full altitude range of low Earth orbit. The results were unambiguous. The current population of intact objects, not just debris, but functional satellites and rocket bodies, already exceeds the unstable threshold at all altitudes between 400 and 1,000 kilometers, and exceeds the runaway threshold, meaning the threshold above which cascade becomes self-sustaining and irreversible. At nearly all altitudes between 520 and 1,000 kilometers, this is the altitude range where the overwhelming majority of operational satellites operate, where Starlink flies, where the International Space Station orbits, where weather satellites, Earth observation platforms, and communications constellations have their infrastructure, and according to the most current stability model available, authored in part by the scientist who first described the problem in 1978, the population density in that range has already crossed the point where cascade is not just possible but structurally likely, given enough time and enough fragmentation events. The European Space Agency's own 2025 report reaches the same conclusion using different methodology. The amount of space debris, ESA states, has to be actively cleaned up. Preventing new debris is no longer enough. And then, in language that makes the implications explicit even without any additional launches, the number of space debris would keep growing. Because fragmentation events add new debris objects faster than debris can naturally re-enter the atmosphere. To prevent this runaway chain reaction, known as Kessler Syndrome, from escalating and making certain orbits unusable, active debris removal is required. What makes the Kessler cascade genuinely different from most environmental crises is the irreversibility. When a forest is cleared, it can be replanted. Slowly, imperfectly, but the process runs in both directions. When a river is polluted, the pollutants can be filtered out. The ecosystem can recover over time. But when the debris density in a given orbital shell crosses the cascade threshold, there is no equivalent reversal process. The fragments produced by each collision are distributed across a range of orbital altitudes and inclinations, increasing the collision probability for every other object at every altitude they pass through. The cascade does not stay in one place. It spreads, and it spreads at speeds that make human response timescales essentially irrelevant. A full Kessler cascade in low Earth orbit would not look like an explosion. It would look, from the outside, like nothing at all, because it happens in a region of space that is invisible to the naked eye and irrelevant to daily life until it is not. Satellites would begin failing at higher rates. Collision avoidance maneuvers would become more frequent, then constant, then impossible to execute fast enough. New launches would become increasingly dangerous. As rockets pass through debris clouds on their way to orbit, eventually, the orbital environment would become so hazardous that no new satellite could be reliably operated there. And since the existing satellites would be failing and burning out, the infrastructure would simply degrade piece by piece over a period of years or decades, until the invisible layer that modern civilization depends on quietly went dark. There would be no single moment of catastrophic failure. There would be a long, grinding degradation, GPS becoming less accurate, then intermittent, then unavailable, weather forecasting losing its satellite data and falling back on ground-based systems with dramatically reduced global coverage, communications networks failing in regions where terrestrial infrastructure is weakest, and through all of it, the fundamental problem would be unsolvable from the ground, because the environment needed to deploy the replacement hardware would be the same environment that had become too hazardous to operate in. Kessler himself, writing in 2009, framed the long-term stakes in terms that have not lost their precision. Our actions in the coming decades will determine whether Earth's orbit becomes humanity's greatest technological achievement or its most enduring prison. The question of how close we are to that prison, how many years, how many fragmentation events, how many launches, is where the mathematics gets both more precise and more uncomfortable than most public conversations about space debris ever acknowledge. Quantifying the risk of Kessler Syndrome is one of the more technically demanding problems in applied mathematics, because it requires modeling the behavior of a population of hundreds of thousands of objects in three-dimensional orbital space over timescales of decades to centuries, accounting for fragmentation probabilities, atmospheric drag at varying altitudes and solar activity levels, and the cascading interactions between debris populations that are themselves changing over time. The models that exist for this purpose are sophisticated, probabilistic, and, with one or two notable exceptions, not widely discussed outside the community of researchers who build them. One of the most rigorous attempts to quantify Kessler risk was the CASIEM model, developed by researchers working on actuarial risk assessment for the space insurance industry. which is, perhaps unsurprisingly, one of the communities with the most direct financial interest in getting the numbers right. The Kessler model is a stochastic simulation of debris and spacecraft in low Earth orbit, designed to answer specific questions about cascade probability over defined time horizons. Its base case scenario, representing current trends in launch activity and debris accumulation, with no significant new mitigation measures, predicts the collapse of the usable low Earth orbit environment within 222 to 258 years from the model's baseline date, or, expressed in probability terms, approximately 1 chance in 3,300 of cascade onset within the next 100 years, rising to a 71% likelihood within 250 years. 250 years sounds like a long time. Long enough, perhaps, to feel like a future generation's problem rather than a current one. But the Kessler numbers assume current trends, not accelerating ones. They assume the launch rate remains roughly constant, which it is not. Commercial satellite constellations have been growing exponentially for the past decade and show no sign of slowing. And they represent the base case, not the worst case. The model's adverse scenarios, incorporating anti-satellite tests, major fragmentation events, or significantly higher launch rates, push the timeline substantially closer. More importantly, the Kessler timescale describes when the orbital environment becomes effectively unusable. It does not describe when it becomes critically dangerous, which is a different and earlier threshold. And it is on that earlier threshold, the point at which the risk of operating in low Earth orbit becomes prohibitively high, not the point at which it becomes literally impossible, that some of the most recent research has produced results that are significantly more urgent. In June of 2025, a research team at Princeton University published an analysis introducing a new metric they called the crash clock, an acronym standing for collision realization and significant harm. The crash clock measures a specific and very concrete thing if every satellite in low Earth orbit simultaneously lost its ability to perform collision avoidance maneuvers. If the operators lost communications, or the propulsion systems failed, or a major solar storm knocked out the command and control infrastructure, how long would it be before a catastrophic collision occurred? Not a small collision, not a manageable fragmentation event, but a collision large enough to seed a cascade, a collision of the kind that would mark the beginning of the end of LEO as a usable environment. When the Princeton team ran this calculation using data from 2018, before the mega-constellation era had fully arrived, the answer was 121 days. With the satellite population that existed at that time, you had roughly 4 months of margin between a total loss of collision avoidance capability and the first catastrophic collision. 4 months to restore communications, fix the problem, re-establish control of the constellation. When they ran the same calculation using data from June 2025, the answer was 2.8 days. Not 4 months. Not weeks. 2.8 days. 7 years of mega-constellation deployment. Primarily Starlink, but also a growing collection of other operators, had reduced the collision-free window from 121 days to less than 72 hours. And even within that window, the risk is not evenly distributed. The Princeton analysis found that if operators lost control for just 24 hours, not 2.8 days, just 1 day, there would be a 30% probability of a catastrophic collision occurring in that window alone. 30%. From a single day of lost communications, the implication is not that catastrophe is imminent. Satellite operators do not lose communications for days at a time under normal circumstances. And the engineering systems designed to maintain collision avoidance capability are robust and multiply redundant. But the crash clock is not measuring normal circumstances. It is measuring the margin available when things go wrong. The buffer between a serious but manageable incident and an irreversible cascade. And that buffer has shrunk by a factor of roughly 40 in 7 years. If the trend continues at even a fraction of its current rate, it does not take long before the buffer disappears entirely. There is one additional scenario that the Princeton team specifically flagged, and that a separate analysis in 2025 identified as the most credible near-term trigger for cascade onset a major solar storm. In May of 2024, a geomagnetic event now called the Gannon storm, one of the most powerful solar storms in 2 decades, caused more than half of all satellites in low Earth orbit to expend fuel on repositioning maneuvers as the heated upper atmosphere increased drag, pulling satellites lower and requiring corrections to maintain operational altitudes. The storm did not cause any catastrophic collisions, but it demonstrated precisely the mechanism that the Princeton model identifies as the most dangerous failure mode. A solar event powerful enough to simultaneously disrupt the communications and propulsion systems of hundreds or thousands of satellites, removing their ability to maneuver, while the atmospheric disturbance increases the density of the debris environment around them. According to the 2025 analysis, a storm of sufficient magnitude could trigger the conditions for cascade onset in less than 3 days. And there would be, in the model's words, less than about 3 days to respond. 3 days. The entire window between a major solar event and the potential beginning of an irreversible cascade in low Earth orbit, assuming current population densities, is approximately 72 hours. That is less time than most international emergency protocols take to convene a preliminary response meeting. The numbers describe a situation that is not yet a crisis, but that has moved, with remarkable speed, from a theoretical concern to an operational reality. And to understand how it moved this fast, you need to go back to a specific date, a specific satellite, and a specific decision that one country made in January of 2007. On the morning of January 11th, 2007, ground stations around the world began detecting something unusual in the orbital environment. The object count in a specific region of low Earth orbit, centered around an altitude of approximately 865 kilometers, in a sun-synchronous polar orbit, was increasing rapidly, in a pattern consistent with a high-velocity fragmentation event. Within hours, the United States Space Surveillance Network had catalogued hundreds of new objects. Within days, the count had grown to more than 1,000. Within months, it exceeded 3,000 trackable fragments, and the estimates for the total debris population produced by the event, including fragments too small to track individually, ranged from 150,000 to more than 300,000 individual pieces. China had destroyed one of its own satellites, a weather satellite called Fengyun 1C, which had been in operation since May of 1999. Was struck by a kinetic kill vehicle launched aboard a ballistic missile from the Xichang Satellite Launch Center, traveling in the opposite orbital direction at a closing velocity of approximately 8 kilometers per second. The two objects met in a head-on collision that released energy equivalent to several tons of high explosive, shattering both the satellite and the kill vehicle into the largest artificial debris cloud ever created in the history of spaceflight. The decision was a weapons test. China was demonstrating anti-satellite capability, the ability to destroy an adversary's space-based infrastructure in the event of a conflict. And the target, a 15-year-old weather satellite in a remote polar orbit, was chosen specifically because it was expendable. The test succeeded, in the narrow sense that the satellite was destroyed and the capability was demonstrated. In every other sense, It was one of the most costly single acts of environmental damage in the history of space exploration. NASA's chief scientist for orbital debris at the time called the Fengyun 1C fragmentation the worst single satellite breakup in the history of the space age. The debris cloud extended from altitudes of less than 200 kilometers to more than 3,850 kilometers, encompassing the full range of low Earth orbit and beyond, reaching into orbital altitudes where atmospheric drag is so weak that objects can persist for centuries. The majority of the fragments settled into mean altitudes above 850 kilometers, where the atmospheric environment is thin enough that decay times are measured not in years but in generations. The long-term persistence of this debris field is not an abstraction. Calculations by NASA's Orbital Debris Program Office, tracking the projected decay of the Fengyun 1C cloud over time, indicated that 50% of the catalogued fragments would still be in orbit in 2025, which is, notably, now, and that 10% of them would still be circling Earth in 2090, 83 years from now. Fragments from a single weapons test conducted in 2007 will still be completing orbital passes, still generating collision risks for every satellite that shares their altitude range, still contributing to the debris density that the Kessler models are trying to calculate. The consequences were not contained to the abstract and the statistical. In January of 2013, 6 years after the Fengyun test, a small Russian laser-ranging satellite called Blitz, orbiting in a polar orbit at an altitude that intersected the Fengyun debris cloud, was struck by a fragment. The impact knocked Blitz out of its operational orientation, sent it spinning uncontrollably, and rendered it permanently non-functional. The fragment responsible was a piece of a Chinese weather satellite that had been destroyed while the operators of Blitz were still in graduate school. One nation's weapons test, conducted in the name of strategic demonstration, had reached across 6 years of orbital time to destroy another nation's scientific instrument, with no warning, no accountability, and no mechanism for remedy. The Fengyun 1C test was not an isolated incident. In November of 2021, Russia conducted its own anti-satellite test, destroying the defunct Soviet-era satellite Cosmos 1408 and generating more than 1,500 trackable fragments, with estimates for the total smaller debris reaching hundreds of thousands of pieces. The resulting debris field passed through the altitude range of the International Space Station and the Chinese Tiangong Space Station, forcing both to conduct emergency procedures. The astronauts and taikonauts aboard both stations had to shelter in docked spacecraft, prepared for emergency evacuation, while the debris cloud spread through their orbital neighborhood. In August of 2024, a Chinese Long March 6A rocket body broke apart in low Earth orbit, creating a cloud of at least 700 confirmed fragments, potentially exceeding 900, in a sun-synchronous orbit that is critical for Earth observation and climate monitoring satellites. The event was not a weapons test. It was an uncontrolled fragmentation caused by residual propellant in an improperly passivated rocket stage, the exact failure mode that space debris mitigation guidelines have been warning about for decades. The rocket stage broke apart on its own, for no external reason, simply because it contained stored energy that eventually found a way to release itself. This is the part of the debris problem that is hardest to communicate, because it requires holding two ideas simultaneously: the deliberate acts, the weapons tests, the reckless launches, the failures to decommission, are individually outrageous and individually consequential. But even if every deliberate act stopped tomorrow, the problem would continue to grow, because the unintentional fragmentation events are built into the physics of the existing population. Old rocket stages contain residual fuel that expands and ruptures, Old satellites have pressurized systems that eventually fail. The debris is not just a record of bad decisions. It is a self-generating system that has developed enough momentum to sustain itself. Against this background, an environment that is generating new hazards faster than it can clear old ones, driven by both deliberate actions and unavoidable physics. The question of how to reverse the trend becomes one of the most complex engineering and governance challenges in the history of space exploration. And it has been made significantly more complicated by a development that, depending on how you look at it, is either the solution or an additional layer of the problem. In May of 2019, SpaceX launched the first batch of 60 Starlink satellites into low Earth orbit, beginning the most rapid deployment of orbital infrastructure in the history of spaceflight. By early 2026, the Starlink constellation had grown to more than 9,000 operational satellites, making it by a significant margin the largest satellite constellation ever assembled, larger than the entire rest of the world's operational satellite fleet combined at the time the program launched. SpaceX produces Starlink satellites at a rate of approximately 8 per day at its manufacturing facility in Redmond, Washington, and launches them on dedicated Falcon 9 missions with a frequency that, in peak periods, rivals commercial airline flight schedules. The scale of what has been built is genuinely difficult to absorb. As of 2025, more than 7,135 of the approximately 11,800 active satellites in Earth orbit are Starlink spacecraft. One company's constellation accounts for more than 60% of all operational satellites in human history. And the program is not complete. SpaceX has regulatory approval to grow the constellation to 12,000 satellites and has filed applications for expansion to 42,000. Starlink is not just a large satellite program. It is a fundamental restructuring of what human presence in low Earth orbit looks like. The operational consequences of this scale are visible in data that SpaceX itself has made public. Between December of 2024 and May of 2025, a period of 6 months, Starlink satellites performed 144,404 collision avoidance maneuvers. That is not a typo. 144,000 times in 6 months. A Starlink satellite detected an approaching object and fired its thrusters to move out of the way, averaged across the fleet and across the time period. That works out to roughly 800 maneuvers per day, or 1 every 2 minutes, continuously, around the clock, every day of the week. And this level of traffic is occurring when the constellation is at approximately 1/5 of its target size. Professor Hugh Lewis, one of the world's leading experts on orbital debris at the University of Birmingham, has calculated that if current trends continue, Starlink satellites alone would need to perform approximately 1 million collision avoidance maneuvers every 6 months by 2028. When the constellation is still well short of its authorized maximum. 1 million maneuvers in 6 months. The automation required to execute this volume of orbital adjustments without human oversight already exists. Starlink's collision avoidance system operates autonomously, using onboard AI to detect threats and execute maneuvers without waiting for ground commands. But the question Lewis and others are asking is not whether the automation can handle the current traffic. It is whether any system, automated or otherwise, can handle the traffic levels that are coming. And what happens the first time it cannot? The answer to the first part of that question is already visible in the risk statistics. A paper published in the Journal of Space Safety Engineering estimated that the cumulative probability of at least one collision involving an active Starlink satellite in any given year is already greater than 10%. 10% per year, over a decade. Assuming no change in constellation size or debris environment, that represents a near certain collision. and each collision at Starlink altitudes would generate thousands of new debris fragments, distributed across the orbital shells that the rest of the constellation operates in, increasing the collision probability for every other satellite in the fleet and for every other operator at similar altitudes. SpaceX is aware of this, and the company's response has been substantive. In late 2025 and into 2026, SpaceX began a major restructuring of the Starlink constellation, lowering approximately 4,400 satellites from their operational altitude of roughly 550 kilometers down to approximately 480 kilometers. The rationale is straightforward at lower altitudes. Atmospheric drag is stronger, which means that a satellite that fails or is decommissioned will decay out of orbit in months rather than years, dramatically reducing the time window during which a dead satellite represents a collision hazard. SpaceX states that the altitude reduction produces more than an 80% reduction in ballistic decay time during solar minimum conditions, the period when atmospheric drag is at its weakest and debris lifetimes are at their longest. This is a meaningful safety improvement, and it represents a level of engineering investment in orbital sustainability that most other operators have not matched. But it is not, by itself, sufficient to stabilize the orbital environment, for two reasons. The first is that SpaceX is not the only operator building mega constellations. China's Qianfan constellation has plans for 15,000 satellites. China's satellite network group's Guowang constellation targets 13,000. Amazon's Project Kuiper is authorized for 3,236. OneWeb, Telesat, and a growing list of national programs are adding thousands more. The Massachusetts Institute of Technology's most recent modeling projects that by the end of 2029, approximately 70,000 satellites could be operational in low Earth orbit, more than 5 times the population of 2019, in a time frame of less than a decade. The second reason is more fundamental, and it is the same reason that the debris problem cannot be solved by simply stopping new launches. The existing population of large debris objects, dead satellites, spent rocket bodies, fragmentation clouds from past events, is already large enough to sustain the cascade process on its own, without any new launches, given enough time and enough uncontrolled fragmentation events. The new constellations add to the collision risk, but they are not the primary source of it. The primary source is the legacy debris that nobody owns, nobody controls, and nobody has yet developed a practical way to remove at scale. There is one more dimension of the constellation problem that rarely gets discussed in public, and it concerns not the satellites themselves, but the act of launching them. Every Starlink satellite that SpaceX builds weighs approximately 575 kilograms. When it reaches the end of its operational life and re-enters the atmosphere, that mass burns up, but it does not disappear cleanly. A study published in the journal Geophysical Research Letters in 2024 estimated that a typical 250 kilogram spacecraft generates approximately 30 kilograms of aluminum oxide particles during re-entry, particles that are too light to fall quickly and may linger in the upper atmosphere for decades. SpaceX estimates that 4 to 5 Starlink satellites re-enter the atmosphere every single day. At that rate, the constellation is depositing tens of kilograms of aluminum oxide into the stratosphere daily. And when the constellation reaches its target size, that number will be proportionally larger. The long-term atmospheric implications of this material flux are not yet fully understood, but the scale of it is large enough that researchers are beginning to ask questions about ozone chemistry and climate forcing that have no established answers. The point is not that Starlink is uniquely villainous. It is not. The point is that operating tens of thousands of satellites in low Earth orbit generates consequences that extend beyond the orbital environment itself. in ways that the existing regulatory frameworks were not designed to anticipate or manage. The debris problem is the most acute of these consequences, but it is not the only one, and the decisions being made right now about how many satellites to launch, at what altitude, with what deorbit requirements, and under what international oversight will shape the orbital and atmospheric environment for generations, which brings the story to the most technically audacious and economically difficult challenge in the history of applied engineering. How do you clean up a junkyard that covers the entire circumference of the Earth, where the garbage is moving at 28,000 kilometers per hour? Most of it is too small to grab, and the whole thing is growing faster than you can remove it. The fundamental physics of active debris removal is not complicated to describe. You need a spacecraft that can match the orbit of a target object, approach it closely enough to capture or interact with it, and then either drag it into a lower orbit where atmospheric drag will complete the deorbit, or attach a propulsion system that guides it to a controlled re-entry. The engineering required to execute these steps reliably, at scale, and at a cost that makes the operation economically viable rather than a one-off demonstration is one of the hardest problems in the current space industry. The difficulty begins with the nature of the debris itself. Most large debris objects, spent rocket stages, defunct satellites, are tumbling, not spinning in a controlled, predictable way, but tumbling irregularly at rates that can range from a few degrees per second to several full rotations per second, in patterns that change over time as residual atmospheric drag and gravitational gradients redistribute angular momentum. A spacecraft approaching a tumbling rocket stage cannot simply grab it. The angular momentum of the rotating object would be transferred to the chaser's spacecraft on contact, potentially sending both into an uncontrolled spin, matching the rotation, or arresting it before capture. Requires either extremely precise robotic manipulation or some form of contactless interaction. Lasers, electromagnetic fields, deployable nets, each of which has its own engineering constraints and failure modes. Then there is the legal dimension, which is in some respects even more complicated than the engineering. Under the Outer Space Treaty of 1967 and subsequent international agreements, space objects remain the property of the nation that launched them, even after they become non-functional debris. Removing another nation's debris without permission is legally ambiguous at best, and potentially a violation of international law at worst. For debris that was launched by nations that no longer exist, Soviet-era rocket bodies, for example, the legal ownership chain is unclear. For debris launched by nations that have strategic interests in preventing their hardware from being examined by foreign operators, the permission question has obvious security implications. The result is a situation in which the largest, most dangerous debris objects, old Soviet rocket stages at altitudes where they will persist for centuries, are the ones for which the political obstacles to removal are highest. Despite these challenges, serious progress is being made at the technology level. The most advanced active debris removal program currently underway is the ClearSpace 1 mission, a collaboration between the European Space Agency and the Swiss startup ClearSpace SA, scheduled for launch in the second half of 2026. The mission will demonstrate the core technologies required for debris removal: autonomous approach, proximity operations, capture of a tumbling non-cooperative object, and control deorbit, using as its target the Proba 1 satellite, a 95-kilogram ESA Earth observation spacecraft launched in 2001 and now defunct. ClearSpace 1 will approach the satellite, match its tumbling motion using vision-based AI guidance systems, capture it with 4 robotic arms developed with ESA technology, and guide the combined spacecraft into a controlled re-entry that destroys both objects in the atmosphere. The mission is, in the explicit framing of both ESA and ClearSpace, a demonstration, a proof of concept intended to establish the technical and commercial foundations for a debris removal industry that currently does not exist. The target was chosen for its relatively known properties and manageable size, and the mission cost, funded at €86 million by ESA with additional commercial investment, reflects the reality that first-of-kind demonstrations in space are expensive. The eventual goal is to reduce the cost per removal to a level where routine debris removal, the 5 to 10 large objects per year that models suggest are required to stabilize the orbital environment, becomes commercially viable. Other technology approaches are moving through earlier stages of development. Starlink-scale, a Japanese company, has developed magnetic capture technology that uses a docking plate installed on client satellites combined with a magnetic grappling system on the servicer spacecraft, a solution that works for objects designed to accommodate it, though not for legacy debris that predates the technology. Ground-based laser systems are being developed that could use high-powered laser pulses to ablate material from the surface of small debris fragments, generating tiny thrust impulses that gradually alter their orbits and accelerate their decay. Japan's EX Fusion startup raised funding in 2024 specifically to develop this ground-based laser debris clearing capability. JAXA, Japan's space agency, launched a wooden satellite called LignoSat in December of 2024, testing the concept of satellites constructed from biodegradable materials that burn completely on re-entry rather than leaving metallic fragments in the atmosphere. All of these approaches have merit, none of them, individually or in combination, are currently capable of addressing the scale of the problem. NASA's modeling indicates that stabilizing the LEO environment over the next 200 years, preventing the cascade from accelerating to the point of no return, requires the active removal of at least 5 large objects per year, continuously, beginning now. As of early 2026, the number of large debris objects that have been actively removed from orbit is 0. The first demonstration mission has not yet launched. The commercial market for debris removal is at a stage comparable to the commercial launch industry in the early 1990s. There is serious investment, serious technology development, serious institutional support. But there is a very long distance between where the industry is and where it needs to be to make a material difference to the trajectory of the debris environment. The cost dimension adds another layer of complexity. NASA's Office of Technology, Policy and Strategy has estimated the cost of active debris removal at between $6,000 and $18,000 per kilogram of debris removed, depending on the mission architecture. At those rates, removing the 50 most dangerous objects in low Earth orbit, a category that is dominated by large Soviet-era rocket stages, each weighing several tons, would cost on the order of several $100 million, stabilizing the environment over the long term, at 5 removals per year for decades, would require sustained annual investment in the billions of dollars. The Kessler model's analysis of what it would take to meaningfully reduce cascade risk suggests that spacefaring nations would need to collectively commit approximately $2 billion to $4 billion per year through 2040, an investment comparable to the annual budget of a mid-sized national space agency, sustained for 2 decades. The cost dimension adds another layer of complexity. NASA's Office of Technology, Policy and Strategy has estimated the cost of active debris removal at between $6,000 and $18,000 per kilogram of debris removed, depending on the mission architecture. At those rates, removing the 50 most dangerous objects in low Earth orbit, a category that is dominated by large Soviet-era rocket stages, each weighing several tons, would cost on the order of several $100 million. Stabilizing the environment over the long term, at 5 removals per year for decades, would require sustained annual investment in the billions of dollars. The Kessler model's analysis of what it would take to meaningfully reduce cascade risk suggests that spacefaring nations would need to collectively commit approximately $2 billion to $4 billion per year through 2040, an investment comparable to the annual budget of a mid-sized national space agency, sustained for 2 decades. There is also the question of what happens to the debris that cannot be actively removed. The 130 million fragments below the size threshold for individual tracking. Too small to grab, too numerous to target, but large enough, collectively, to degrade the orbital environment steadily over time. For this category of debris, the only viable long-term strategy is prevention, ensuring that future satellites and rocket stages are designed to minimize fragmentation risk, are properly passivated at end of life to eliminate residual energy sources, and are operated in orbits low enough that atmospheric drag removes them within a manageable time frame. The engineering standards for achieving this exist. ESA's 5-year deorbit rule, requiring all satellites in low Earth orbit to re-enter within 5 years of mission completion, represents the current state-of-the-art in debris mitigation policy. The challenge is not knowing what to do, it is ensuring that every operator, in every jurisdiction, is held to the standard, and that the standard itself keeps pace with a launch rate that is growing faster than the governance infrastructure can track. That investment has not been made. The international governance framework that would allocate it, distribute the costs fairly across spacefaring nations, and enforce compliance with debris mitigation standards does not exist. The Zero Debris Charter that ESA launched, a voluntary commitment signed by 19 countries and more than 150 organizations to minimize debris generation from future missions, is a meaningful step, but it is a voluntary commitment to future behavior, not a mechanism for cleaning up what already exists. The gap between what the physics requires and what the international community is currently doing is enormous, and it is not closing at anything resembling the required speed. And yet, there are reasons to believe that the situation is not hopeless, or at least, not inevitably hopeless. Because while the debris problem is real, urgent, and currently on a trajectory that the science does not endorse, the alternative trajectory, the one where the problem is actually solved, also exists. And the decisions that determine which trajectory the world is on are being made right now by governments and companies and international bodies in ways that are more visible and more tractable than the problem itself might suggest. Before moving to the question of solutions, it is worth sitting for a moment with the full scope of what is actually at stake. Because the common framing of the Kessler problem as a threat to space exploration and satellite services undersells the depth of the dependency that modern civilization has built on orbital infrastructure. GPS, in the public imagination, is primarily a navigation tool, the thing that tells you how to get from one place to another, the system that backs up the map on your phone. But GPS is also a timing system, and its timing function is the one that most of the world's critical infrastructure runs on. GPS satellites broadcast extraordinarily precise time signals, accurate to within about 100 nanoseconds, that are used to synchronize everything from mobile phone networks to financial trading systems to power grids to internet routing protocols. When financial exchanges execute trades, the timestamps they use are GPS derived. When mobile networks hand off connections between cell towers, the synchronization they rely on is GPS derived. When power grid operators coordinate the phase of alternating current across hundreds of kilometers of transmission lines, The timing reference they use is GPS-derived. When emergency services dispatch responders, the coordinates they use are GPS-derived, 100 nanoseconds of timing precision, delivered continuously by 24 satellites in medium Earth orbit. Underpins a larger fraction of the global economy than most people who depend on it have ever been asked to consider. The loss of GPS would not primarily be experienced as an inability to navigate. It would be experienced as a cascading synchronization failure across systems whose dependence on precise timing most of their operators do not fully understand. Because the timing infrastructure runs silently in the background and nobody thinks about it until it fails. The degree to which modern digital infrastructure is GPS dependent is, in a specific and important sense, unknown, not because it has not been studied, but because the interdependencies are complex enough that a full accounting of what would fail, and in what order, and with what secondary effects, is beyond the modeling capacity of any single organization. What is known is that major GPS outage simulations, run by governments and financial regulators, consistently produce results that are described as alarming by the people who run them and then classified by the people who receive the results. Weather forecasting is a clearer case. Polar orbiting weather satellites provide 85% of the input data for global atmospheric models. Those models are the foundation of every weather forecast issued anywhere in the world. From the 3-day outlook on your phone to the seasonal predictions that agricultural systems use to plan planting and harvesting. The accuracy of modern weather forecasting, which has improved so dramatically over the past 3 decades that a 5-day forecast today is more accurate than a 3-day forecast was in the 1980s, is almost entirely a product of satellite data. Remove that data, and the models lose most of their predictive skill. The immediate consequences would be measured in agricultural losses, in storm systems that strike without warning, in shipping routes that cannot be planned, in the slow degradation of every system that depends on knowing what the weather will do next. And then there is the category of consequences that is hardest to quantify, but may be most important in the long run: the loss of the ability to access space at all. A full Kessler cascade in low Earth orbit would not physically prevent objects from passing through. The debris would not form a solid barrier, but it would make the probability of a collision during any given transit high enough that launches into low Earth orbit would become economically and practically untenable. Rockets can be shielded against small debris impacts to some degree, but not against the tens of thousands of fragments larger than 10 centimeters that would populate a post-cascade LEO environment. The insurance cost alone for a launch vehicle passing through a fully cascaded debris shell would be prohibitive, and that is before accounting for the engineering challenge of building a spacecraft that can survive passing through that environment and then operating within it. The consequence is not just the loss of current satellite services, it is the permanent loss, on timescales of decades to centuries, of the ability to deploy new infrastructure to replace them. Satellites have operational lifetimes. A GPS satellite, properly maintained, may operate for 15 to 20 years before requiring replacement. If the orbital environment becomes too hazardous to launch into before a generation of GPS satellites reaches end of life, there is no mechanism for restoring GPS service. It simply degrades and eventually disappears. And there is no ground-based alternative capable of replicating its global coverage or its timing precision. This is the scenario that distinguishes Kessler Syndrome from most other environmental crises. It is not just a problem that damages existing systems. It is a problem that removes the option to fix them. The cage, once closed, does not just trap what is inside. It removes the ability to put anything new in from outside. And in a civilization that has built its infrastructure on the assumption of indefinite satellite access, the closure of that option would represent a kind of technological regression that has no precedent in the modern era. Given all of this, the debris, the cascade risk, the timelines, the stakes. The natural question is whether there is any realistic path to a different outcome. And the honest answer, which the science supports, but which the headlines rarely frame clearly, is that there is. But it requires things that human institutions are not historically good at doing under conditions of distributed incentives and diffuse long-term risk. In 2024, something happened in the management of Earth's orbital environment that had never happened before. For the first time in the history of space operations, the number of objects re-entering Earth's atmosphere in a controlled manner, meaning deliberately deorbited by their operators at the end of their mission lives, exceeded the number that re-entered uncontrolled, meaning they decayed on their own schedule without any human guidance. This is a small milestone, easily overwhelmed by the scale of the ongoing debris accumulation problem. But it is the kind of directional indicator that is worth noting, because it marks a genuine shift in operational norms. Approximately 90% of rocket bodies that reached end of life in 2024 complied with the established 25-year re-entry guideline, meaning they were placed in orbits low enough that atmospheric drag would bring them down within 25 years of their final mission. 80% already met ESA's newer, more demanding 5-year standard. Commercial satellite operators are increasingly deploying their constellations at lower altitudes, below 500 kilometers, specifically to ensure that failed or decommissioned satellites re-enter quickly rather than accumulating as long-lived debris. The operational culture of the commercial space industry has changed over the past decade in ways that are substantive and measurable. The ESA Zero Debris Charter, which commits its signatories to the goal of zero debris generation from space missions by 2030, has been signed by 19 countries and more than 150 organizations. It is voluntary, its enforcement mechanisms are limited, and its ambition is not matched by the current trajectory of the debris population. But voluntary commitments, in the history of environmental governance, are sometimes precursors to binding regulation, and the international conversation about orbital debris has reached a level of seriousness and specificity that it has never had before. The 9th European Conference on Space Debris, held in Bonn in April of 2025, brought together scientists, engineers, operators, industry experts, lawyers, and policymakers from across the world for a gathering whose size and institutional seriousness would have been unimaginable 10 years earlier. The technical solutions are not lacking, they are underfunded, insufficiently scaled, and operating in a governance vacuum that makes coordinated action difficult. But the engineering is understood, the proof of concept work is underway, and the commercial case for debris removal is becoming clearer as the costs of operating in congested orbits continue to rise. The active debris removal market was valued at $569 million in 2024 and is projected to grow to $3.5 billion by 2035. That is not yet the scale required to make a material difference to the debris population, but it is growing, and it is being driven by the same economic forces that made the debris problem worse in the first place. The commercial incentive to keep orbits usable and valuable. The most fundamental challenge is not technical and not economic. It is the structure of the incentive problem, the specific form of the tragedy of the commons that the orbital environment represents. No single operator has sufficient incentive to unilaterally invest in debris removal at the scale required, because the benefits would accrue to all operators equally, while the costs would fall on whoever acts. Every operator benefits from clean orbits, but every operator also benefits from launching their satellites before the regulations tighten, from deferring deorbit investments until they are legally required, from treating the orbital commons as a resource to be used rather than a heritage to be stewarded. The rational response to this structure, for any individual actor operating within it, is to do the minimum required and wait for others to bear the cleanup costs. The aggregate result of everyone following this rational logic is the debris environment that currently exists. Breaking out of this structure requires either a binding international agreement that changes the incentive calculus for all operators simultaneously, or a regulatory shift in the major spacefaring jurisdictions. The United States, Europe, China, Russia, that internalizes the cost of debris generation into the economic model for space operations. Neither of these things is easy, or fast, or likely to happen without sustained political pressure and institutional change. But neither is unprecedented. The Montreal Protocol, which successfully addressed the depletion of the stratospheric ozone layer, was a binding international agreement that changed the incentive structure for an entire industry. Within a decade of the scientific consensus being established, the governance challenge of orbital debris is not simpler than the ozone problem, but it is not obviously harder either. What is different about the debris problem is the asymmetry of the consequences. With ozone depletion, the damage was reversible. The ozone layer has been recovering since the protocol took effect. With orbital debris, past a certain threshold, the damage is not reversible on any timescale relevant to human civilization. The cascade, once started, runs on its own physics, which means that the governance challenge has to be solved before the threshold is crossed, not after. Because after is too late. Donald Kessler, who spent 47 years watching the problem he identified in 1978 grow from a theoretical concern to an operational reality, framed the choice in terms that have not aged. We are building something in orbit that could become either humanity's greatest technological platform or its most enduring prison. The difference between those two outcomes is not a question of technology. The technology exists. It is a question of whether the international community can organize itself to act on a problem that is serious, urgent, and just invisible enough that the urgency never quite breaks through into the sustained political attention that real solutions require. That question has no clean answer tonight. The debris is real. The cascade risk is real. The crash clock is at 2.8 days and falling. The timelines that the models produce, 250 years to probable cascade onset under current trends. But critical density thresholds in key orbital shells, possibly within 50 years, are not comforting numbers, but they are also not zero. There is time, there is technology, there is a growing body of scientific consensus, institutional investment, and international conversation pointing in the direction of solutions. What there is not yet is the sustained collective will to act at the scale the physics requires, and the window in which that will can make a decisive difference. The window between the debris environment as it currently exists and the debris environment as it would exist after a cascade has started is narrower than it has ever been, and narrowing faster than it ever has before. There is something worth pausing on in the specific shape of this problem, in the way it is structured, which is unlike almost every other large-scale environmental challenge that humanity has faced. Climate change is visible, it's felt, measurable in the daily experience of weather and temperature and the slow transformation of coastlines. Ozone depletion produced measurable increases in ultraviolet radiation, detectable health effects, ecological impacts that were undeniable once you knew where to look. Both of those problems arrived with evidence that was impossible to ignore for anyone paying attention. And the political response, however slow, however insufficient, was eventually driven by that tangible, experiential evidence. The orbital debris problem produces no such evidence. The sky looks the same from the ground. The satellites continue to work, right up to the moment they do not. The fragmentation events happen silently, in a region of space that is invisible to the naked eye and irrelevant to most of human experience. The cascade, if it begins, will not announce itself with a visible explosion or a perceptible change in the atmosphere. It will announce itself as a slowly increasing failure rate for satellite services that most people assume are permanent features of the technological landscape. And by the time that failure rate becomes undeniable, by the time the GPS dropouts are frequent enough to notice, the weather forecast accuracy has degraded enough to measure, the internet connectivity has become unreliable enough to complain about, the cascade will have progressed to a point where the options for response have narrowed dramatically. This asymmetry between the invisibility of the problem and the magnitude of the consequences is, perhaps, the most genuinely frightening thing about Kessler Syndrome. Not the physics, which is tractable, not the engineering, which is difficult but understood, but the simple human difficulty of organizing a serious response to a serious problem that you cannot see from where you are standing. The morning that starts this story, the one where everything stops, where the GPS is dark and the weather satellites are silent, and the chain reaction that nobody caught has already run past the point where it can be reversed. That morning is not inevitable. The science is clear that it does not have to happen. The technology to prevent it either exists or is being developed. The economic case for clean orbits is understood by the operators who depend on them. The international institutions capable of coordinating the required response are imperfect but functional. None of the obstacles are insurmountable, given sufficient attention and sufficient will, but they are not surmountable on their own. They do not resolve themselves. The orbital environment does not clean itself, and the debris population does not spontaneously begin declining without active intervention. The institutions do not convene without political pressure. The investment does not materialize without clear accountability. The governance frameworks do not emerge without deliberate construction by people who understand the stakes and are willing to make the argument for why those stakes matter, to audiences that would prefer to be thinking about something closer to home. The cage is not closed. The bars are not yet complete. The window is still open, but the window is smaller than it was 7 years ago, and smaller than it was the year before that. And the rate at which it is closing is not something that the current trajectory of launches, mitigation compliance, and international cooperation is going to reverse without a deliberate change in direction. Donald Kessler is in his 80s. He published his original warning in 1978, watched it be acknowledged and underinvested in for 40 years, and published a new assessment in 2025, concluding that the population has already crossed the thresholds he originally warned about. He has been right about the physics for nearly half a century. The question of whether the world will act on what the physics requires is not a question that the science can answer. It is a question that belongs to the people who live under the orbital shells, who depend on the satellites, and who will inherit whatever version of the sky the decisions made in the next decade produce. That is, in the end, what Kessler Syndrome actually is. Not a space story, not a satellite story, not an engineering story, but a story about what happens when the consequences of collective decisions accumulate silently in a place where no one is looking, until the moment when someone looks up and realizes that the ceiling above them has been quietly filling in, piece by piece, for 60 years. The ceiling is not closed yet, but the question of whether it stays open is one that the next 10 years will go a long way toward answering.